gravitational waves on the cosmic microwave background. Let me first make it very clear that I do not claim any authorship of anything I'm giving here. It's just a compilation of a number of papers I used and a few talks which are available online. Also some references from Adam Falkowski's blog. And there are hardly any in fact there are hardly any pictures I have made myself. I've stolen most of the things in a brutal way from other people's talks. But there is a few mine. So let me first give a short introduction of the Bicep2 experiment, what they actually measured, what kind of equipment they had. Then I will discuss the physics of the cosmic microwave background and why actually the cosmic microwave background is polarized, at least partially. Then I will return to after I discuss the physical principles, I will return to the Bicep2 experiment and present their results and their claims. And in the last part, I will discuss the criticism of their result, because it seems that in the scientific community it has encountered a lot of disbelief and criticism as a premature announcement. And let's see what happens next. So, first of all, what is Bicep2? Actually, it's a telescope. A telescope observing the sky in the microwave range of electromagnetic radiation.
What does it mean, biceps?
Bicep? Nothing. Biceps, yes, biceps. So, they state explicitly on their webpage that this is not an abbreviation or a PAN, it's just a name. No, it's not. Actually, it's not. It's just a name. Or at least according to their webpage. So they observed the sky at the 150 gigahertz band. In fact, a band of the width of around, I think, 50, centered around 150 gigahertz. The telescope is ground-based, so it's not like the Kobe, WMAP, or Planck satellite missions where they measure the whole sky and the cosmic microwave background there. It's a much more modest experiment. They just put a telescope on the South Pole. Here is the. So this is a building which hosts a number of astrophysical experiments, and Bicep2 is just one of them. So what they do is to observe the sky in this microwave range. The detector is polarization sensitive, so it measures two polarizations separately. And they observed a small patch of the sky, 90 degrees by 20 degrees approximately, a rectangle on the sky, during 3 observational seasons. So it's a telescope which constantly watches a rather small patch of the sky, around 2% of the whole solid angle. The detector is supposed to detect a very faint signal. Let me remind you that the cosmic microwave background itself is more or less a black body radiation with the temperature of around 3 Kelvin, so it's a faint signal. Moreover, the polarization of the signal is also very small. So the physics of the detection is quite interesting. So in their focal plane, instead of a standard CCD camera or the pupils of an observer, we have a couple of arrays of slot antennas which detect the microwave radiation, and the signal from these antennas is detected by a very sensitive bolometer made of a transition edge sensor read out by a superconducting device. I will say briefly more about that. The goal of the mission was to measure the polarization of the cosmic microwave background, or to say more precisely, to measure the variation of the polarization in the 1 degree scale. I will say later why this scale is important here, but what they did was to measure the polarization of the CMB as accurately as possible in this patch of the sky, and to look at the variation in the 1 degree scale. So this is an American, mostly US-based collaboration with some contributions from Canada, funded by the National Science Foundation. It's a part of a larger collaboration. In particular, Bicep2 is the second telescope they have assembled there. The previous one also observed the same patch of the sky, but with much less sensitivity. And let me stress that their experiment is not the only one which is looking at the polarization of the microwave background and the variation of this polarization. The Planck collaboration is, I think, their main competitor. But on top of that, the CAC array experiments which is also based in the same building, is working exactly on the same problem. So let me just show a few pictures on their webpage what their telescope looks like. So it's basically a telescope, a tube made of metal. I don't remember what metal. It has an objective lens on the front, made of, I think, polyethylene. Something which is which works as lens for the microwave radiation. One important difference from the standard optical telescopes is that the lower part of the telescope has to be kept in cryogenic temperatures. So this red part is kept in 40 degrees Kelvin, whereas the focal plane assembly, the detector itself, is kept at even lower temperature of, I think, 0.2 Kelvin. It has to be kept at such low temperatures because you're detecting signal which is around 3 Kelvins, and you want to see time variations of that. So there is no hope to detect that without going into so low temperatures. The focal plane assembly consists of four arrays, which are in turn composed of, if I remember, 256 pixels, and the pixels are composed basically arrays of antennas. These are basically conductors. I don't remember what they are made of. Detecting the microwave radiation in two polarizations. These antennas are connected together by appropriate lines. The signal then passes through a filter which filters out everything except for this 150 gigahertz range. And then the signal goes through a resistor, which just by ohmic heating, so the resistor is based on a heat island, a part of the telescope which is very well thermally isolated from the rest of the setup. Then the signal, the ohmic resistance just produces heat if there is a signal. And basically the detector is just a very, very sensitive thermometer which measures the temperature of this resistor. This thermometer is basically a piece of superconductor. I don't remember what exactly it is, which is kept very close to its transition temperature, where the sensitivity of the resistance on the temperature is very high. It is biased all the time by a small current which passes through it, and if it is heated, the current drops down very quickly, and the variations of the current are themselves measured by a superconducting quantum interference device, by a squid, or rather an array of squids. So this is the way the detector works. So first of all, so now I want to go to the, I want to make a short discussion of the physics of the cosmic microwave background, just to tell you why we should actually expect the CMB to be polarized. So as it is often said, the cosmic microwave background, which we observe over the whole sky, is basically, to a great degree, a perfect black body radiation. And as we know, the black body radiation is not polarized, because it has no reason to be. It's just light which is in It's just photons which are in thermal equilibrium with matter, and there is no reason for them to be polarized. So where does the polarization come from at all? Okay, so let's go back to the history of the universe, and especially to the early stages when we already, when the matter in the universe is mostly in the form of a high temperature plasma. Let's say that we are after the primordial nucleosynthesis, so this plasma consists mostly of hydrogen, but also helium and a bit of higher elements. The temperature is high enough for this plasma to be completely ionized. So there are no atoms yet, these are just free ions in high temperature plasma, and of course a number of electrons. And it is known that this medium is not transparent to the electromagnetic light. It's opaque. Photons cannot travel there freely. They are just scattered too often. This means that the photons are in thermodynamic equilibrium with the baryons, hot baryons. It is known that this plasma is not exactly uniform. From the very beginning, there were various density and homogeneities there. They are in turn thought, if you believe in inflationary scenarios, they are thought to be remnants of quantum fluctuations of the gravitational field in early stages, which have been just blown up to larger scales by inflation. But even if you don't think about inflations, it's just that this medium was not perfectly homogeneous. And now, there is something important which we have to discuss now, namely the baryon acoustic oscillations. So, let these green dots correspond to baryons. Basically in the form of ionized hydrogen, deuterium, helium, and perhaps a bit some lithium. Let's imagine that there is a slightly overdense region somewhere in this medium. Of course, we can understand the situation just using the Newtonian analogy. There is no need to put new relativity here. Basically, there is a gravitational potential well forming just because this material is more dense. This well attracts matter from the surrounding regions. This way, growing even denser, and the well is becoming even deeper. But this doesn't happen. This cannot happen for an infinitely long time, because as the baryons fall into the well, the average energy of the baryons in the well, which is translated to temperature, goes up. On the other hand, the temperature of the regions where we see rarefaction goes down. It's smaller than the average. Now, of course, higher temperature means higher pressure of the baryons, but it turns out that at this stage of the universe, the pressure of the baryons is negligible when compared to the pressure of the radiation. So, as the temperature goes up, the electromagnetic radiation, the black body radiation the temperature of the black body radiation goes up, and also the pressure of the radiation goes up. And at some point, the gradient of this pressure overcomes the gradient of the gravitational potential, and the flow may reverse. Altogether, what we see are obviously oscillations. And it turns out that you can understand this situation as basically the propagation of waves through this medium with the standard dispersion relation that the frequency is proportional to the wave vector, with the velocity being a fraction of the velocity of light, around 0.5. So the bottom line is that the inhomogeneities of the distribution of matter tend to oscillate as in time with appropriate frequency proportional to their wave vector.
What is the wavelength of this?
So there are various wavelengths here. So
yeah, but this one, which is drawn on the picture.
I would say that this is
Here,
this one.
How big is it?
Well, basically, it is thought that these inhomogeneities have all possible sizes. There is just a spectrum of them.
and it depends on the age of the universe.
So of course they tend to grow.
No, however, I should imagine rather a parsec or a millimeter or what?
There's a full spectrum of them, which is more or less scale
Okay, but
invariant.
we concentrate on. I have to something concrete to be able to think about.
Okay, so let's go for it. Perhaps we will find something. Okay, now there is something very, very important which happens here. Namely, you need to realize that at some point the temperature of the medium goes down and the atoms begin to form. And that's a very important moment in the history of the universe, because as normal atom forms, there are no free charges wandering in the space anymore, and the electromagnetic radiation may just travel over very long distances without any scattering. So at some point, the radiation decouples from the matter, simply because of their combination, because the electrons and ions form electrically neutral atoms. And it turns out that this moment, this transition period is very, very short. It's just a moment when you compare it to other time scales. So at some point, this whole mechanism of oscillation is stopped. And secondly, you need to realize that these oscillations have begun at some point earlier in time, sometime after the inflation. So on this picture, it's suggested that it began actually during the inflation. I've read also otherwise. The whole point is that there is a finite and a well-defined time over which these oscillations take place, and at some point they're just stopped because there is no pressure anymore. What does it mean? Well, first of all, you have to realize that all of these inhomogeneities begin as density inhomogeneities without any large fluid motion. So they begin at the same phase. And then all of them are allowed to evolve over a well-defined finite period of time. It means that various modes of this initial perturbations will evolve somewhat differently with this time. Those whose period corresponds to basically 380,000 years will just evolve a full cycle. Some of them will evolve a half of the full cycle. On the other hand, some of them will stop at some other less defined phase of their evolution. The thing is that those which stop at other points of their evolution rather than the full period or a half period will be damped, because obviously after a full period of the evolution, the density contrast is as pronounced. This is the maximum of the pronouncement of the density contrast. So, what does it mean? Well, it means that a number of after this time of evolution, some of the modes will be very pronounced, others will be damped, just because we allowed only a finite time evolution of these oscillations. And this has very important consequences on the cosmic microwave background. Namely, shortly before the last scattering, the recombination, at the moment of the recombination, some parts of the universe will be denser and hotter, others will be colder and less dense, and there are well-defined sizes of some of the modes will be more pronounced than others. Now, if we look at this structure at a much later time, okay. After the recombination, the photons are basically allowed to travel freely through the universe, and after another 14 billion years, we detect them on Earth. various sizes of these modes, of these oscillating modes, now translate to various angular sizes of structures we see on the sky. If we lived in a completely flat universe, it would simply be the proportionality of simply the angular size times the distance from us to that place would give us the size of the structure. Because the universe has a more complicated geometry, this is a much more subtle thing, but still a particular size of structures of inhomogeneities at this moment corresponds to a particular angular size of the structure we observe in the sky. And now, if it is so, we may look at the cosmic microwave background. This is basically a snapshot of the universe, more or less at this recombination time. We can decompose its inhomogeneities in the spherical harmonics, and what we will see will be certain peak. It will be a complicated structure with a number of peaks. These peaks basically correspond to the modes which manage to either evolve their full cycle of a full period during the early stages of the universe, those which manage to evolve half of it, and so on and so on and so on. This pattern is exactly what was observed over the last 20 years, and it's something extremely important because it turns out that you can read out many cosmological parameters just from the position of these peaks and their relative sizes. So there were many missions dedicated just to looking at the variation of the temperature of the cosmic microwave background and the power spectrum of these variations, simply because you can read out various data concerning the universe we're living in just from the position and the size of these peaks. Okay, but I haven't discussed the polarization yet. So where does the polarization of the cosmic microwave background come from? The main physical mechanism is simply the scattering of the radiation on free electrons. Without quantum mechanics, you could just think about Thomson scattering. So basically you've got, so imagine just a polarized plane wave coming from this direction and a single electron here. As the wave approaches the electron, it starts to oscillate itself and emits scattered light. But the important thing is that the light is not emitted in the direction of the oscillations, only in the perpendicular directions.
Because the electron acts like an antenna.
Exactly. It's basically a dipole antenna. You've got current flowing in one direction and then reversing and so on and so on. So the radiation is scattered only in this plane, not uniformly actually, but it doesn't matter. The thing is that it is not scattered in this plane if it is polarized in the horizontal direction. But the thing is that at the recombination stage, we don't see just a plane wave approaching an electron. We see a lot of radiation coming from all possible directions with all possible polarizations scattering on electrons. And of course, this does not produce any net effect of polarization, because of course a wave polarized in this direction coming from here will produce only light polarized, will only produce scattered light polarized in the vertical direction. But there is usually equal amount of radiation coming from the top, which will produce the necessary and completely equal radiation polarized in the perpendicular direction. So whenever we've got isotropic radiation coming from all sides, the Thomson scattering doesn't produce any polarization. But something interesting happens if, for some reason, this incoming radiation is not perfectly isotropic. So let's now imagine that there is a bit more radiation coming from here than from here. In that case, more radiation will scatter, more polarized radiation in the vertical direction will be produced than the amount of radiation produced in the and polarized in the vertical direction, simply because there is more energy coming from here than from here. So the bottom line is, if we have just uniform radiation coming from everywhere else, Thomson scattering doesn't produce any interesting effects. But if there is an anisotropy of the radiation coming from various directions, then the scattering on free electrons may produce a slight net polarization. Linear polarization, of course. Now, if you're sitting right in the middle here, you can measure the power of the radiation coming from all directions, then use the spherical harmonic decomposition of this power, and it turns out that the lowest type of anisotropy which produces any effects is the quadrupole anisotropy. So a dipole anisotropy in which there is just more radiation coming from the from this side than from that side does not lead to any net linear polarization. The anisotropy has to be at least quadrupole. Okay, so let's think about the last scattering. So at some moment, the photons of the cosmic microwave background undergo their last scattering before being able to travel freely through the universe. If they gain some net polarization at that moment, this polarization will leave an imprint on the whole pattern on the sky, and this pattern will be basically unaltered. Now, let's imagine we are somewhere here. For various reasons, at the moment of the last scattering, the incoming radiation may be slightly anisotropic. This might lead to various polarization, slight polarization of the microwave of the radiation, and then as we observe various parts of the sky from the Earth, we will see various polarizations. We will see different polarizations at different parts of the sky. That's basically the mechanism. So if there is anisotropy at the moment of the last scattering, and this anisotropy is different in different places of the universe, then this may lead to net polarization of the incoming cosmic microwave background today. But where does this quadrupole anisotropy come from? Well, there are various possible mechanisms. The simplest one is the temperature inhomogeneity. As we discussed, this medium, the plasma we discussed is not completely homogeneous. There are temperature variations there. So imagine we are sitting at a place which is slightly colder than the regions above and below. So in that case, we may expect the radiation coming from the directions of the colder part to be slightly redshifted and also slightly less intense than the one we see coming from the hotter regions. And it turns out that this gives rise to a quadrupole anisotropy. Basically, we see slightly warmer radiation coming from the ceiling and from the floor. Slightly redshifted radiation coming from the vertical regions, and this corresponds basically to n equal 0 quadrupole inhomogeneity. But that's not the only mechanism. Another possible mechanism would be just the vorticity of the medium. If the medium has a non-vanishing vorticity, then an element of the plasma sees the radiation coming from here slightly blue-shifted, just because of the Doppler blue shift. On the other hand, the radiation coming from this part of the medium would be slightly redshifted. This gives rise to an m equal 1 quadrupole anisotropy. Now, it turns out that the vorticity is very strongly suppressed in this medium. It vanishes very quickly, so we expect that at the moment of last scattering, the plasma has very small vorticity, and this mechanism plays no role in the creation of the cosmic microwave background polarization. The third mechanism, and the one which is most important for our purposes, is the cosmic microwave background polarization due to particle anisotropy because of the gravitational waves. Now imagine that there are gravitational waves passing through this medium. The gravitational wave stretches all physical distances in one direction and shrinks them in another perpendicular direction. So this wave passes, let's say, in the vertical direction from bottom to the top. It goes up here, and at a given moment, all distances in these directions are stretched. All distances in this direction are shortened. The net result is that the energy of the photons coming from this direction is smaller because they have been stretched. The wavelength is longer than imagined it to be, longer than average. On top of that, also the intensity is smaller because you can think that the number of photons per unit length is slightly smaller, exactly because the distances have been stretched here. The opposite thing is happening in this direction here. So a gravitational wave produces, again, an quadruple anisotropy in the electromagnetic radiation corresponding to m equal to 2. So these are the two most important mechanisms leading to the anisotropy of incoming radiation at the moment of recombination. Okay, but how can we distinguish? Imagine that we now measure the polarization of the cosmic microwave background. How are we supposed to distinguish between those two constituents? Now, it turns out that it is possible to do it if you are clever. Namely, imagine that we have measured a small patch in the sky. We have measured the temperature variations of the cosmic microwave background, and we also measured the polarization of the electromagnetic waves. What we see is a pattern looking more or less this way. The polarization corresponds basically to a symmetric 2x2 tensor here. It turns out that this tensor field can be decomposed into two modes, so-called E and P modes. I don't like these names, but somehow they pop up. They have nothing to do with the electric and magnetic field. The E mode simply corresponds to the part of this tensor field which is invariant with respect to taking the mirror image. On the other hand, the B part the B part of this polarization is the part which flips its sign when you perform the mirror imaging here. The precise definition is done via the decomposition into the spherical harmonics.
I think it has something to do with the separation into electric and magnetic, because electric field is a vector and V is not a vector, but it's a...
That's true. That's true.
That is what...
That's basically what is meant here. The thing is that these lines here are not vectors. The polarization measured on the sky is not a vector. It does not have a direction. It's just a direction in the sky. So yes, in that sense, this is true. I would just call it the chiral and the non-chiral part of the polarization tensor. That would be a better name, but this is the name that caught up. The thing is that you should not think of the E part as something corresponding to the electric part of the electromagnetic light, and this corresponding to the magnetic part. No, it's just a way to decompose this 2x2 tensor which you measure on the sky. I found a very nice paper about this decomposition. The authors claim that you can actually distinguish these two these two modes by naked eye, indeed you can see that. So this is the full signal. This is its decomposition into E and B modes, and you can see that B modes have certain swirls with a given chirality here. If you look very carefully at this pattern, there is a swirl here, here. Whereas the swirls here do not have chirality. They're just achiral. Okay, so let's imagine we have decomposed our polarization into the E and B modes. Now it turns out that the E modes are absolutely dominated by the scalar perturbations, that is the temperature and anisotropy signal. And of course, the temperature and anisotropy signal is probably, and of course the power spectrum of the E mode is therefore very similar to the power spectrum of the temperature variation in the CMB. Namely, it has a number of peaks, peaking around L equal to 1000. So in a way, it just doubles the information we have already from the temperature variations of the cosmic microwave background. It doesn't introduce much new. Except that the polarization is very slight, so the signal is much smaller. Now, the B modes basically originate only from the gravitational waves. However, this is only true at the moment of the recombination and shortly afterwards, because after the recombination, the light has to travel for another 14 billion years, and as it travels, it undergoes also slight gravitational lensing on the largest structures of the universe. And gravitational lensing is and the gravitational lensing causes a slight displacement of all of these photons. Basically, if you have something very heavy here, the photons will slightly displaced outwards from this heavy, let's say, galaxy cluster. This is a nonlinear transformation of this polarization tensor, of course. So it will somehow mix these two E and these two modes, E and B, and it turns out that this causes a conversion of part of the E spectrum into the B spectrum. So one part of the B spectrum looks basically like the E spectrum, except that it's smoothed out and powered down by a factor of 100. And on top of that, there is the original contribution from the gravitational waves passing through the medium. Fortunately, so it's even weaker than that, but fortunately it's peaked around a different L number, namely 100. So the angular size of the ripples created by gravitational waves is around 1 degree, whereas the ripples created by temperature anisotropy is of the order of 0.1 degree. And this is the only reason why we are able to see this gravitational wave signal. So, Bicep2 is not the first mission which measured the polarization of the cosmic microwave background. It was done first by the Dassey experiment in 2002. But it measured only the E mode, which is much larger than the B mode. Then there was a number of other experiments which measured the pattern of the polarization more accurately with better angular accuracy. As for the B modes, they have only been measured themselves in 2013 by 2 collaborations, but those collaborations did not claim any detection of the gravitational waves in their spectrum. It is only Bicep2 which claims to have measured exactly the signal corresponding to the gravitational waves. Let me stress that this signal is very, very small. I found a very nice plot on one of the publications I read. This is basically variation of the temperature. So in the field of the analysis of the cosmic microwave background, it is customary to measure all these variations as the variations of temperature of the cosmic microwave background. So it's measured in microkelvins. What you see here on this black line are just the variation of the temperature of the microwave background itself, without any polarizations, just the full thing. You can see that it's by itself pretty small and it has this nice peak structure. Forget about the green line. The blue line is the E-power spectrum. It looks basically like the power spectrum of the cosmic microwave background anisotropy, except that it is much smaller than the variation of the CMB. And the B signal is even smaller than E. It is dominated by a part which is basically a copy of the E signal. This is exactly the E signal distorted by the gravitational lensing, except for a small part around the 100, L corresponding to 100, where we see an excess due to gravitational waves. And the Bicep2 claims to have measured exactly that part of the signal. Let me just say that it is also customary in the cosmology to measure the strength of the signal due to gravitational waves by so-called tensor to scalar ratio. It's basically the ratio between the energy contained in the gravitational waves compared to the energy contained in the variation of density and temperature. Okay, so let me first show the raw results of Bicep2. So this is the patch of the sky they were observing. This is the polarization. They already decomposed their measurements into the E part and the B part. And here on the right-hand side you can see simulations which they have created, assuming that the E part is only created from the temperature anisotropies plus some random noise, and the B part is also only the temperature anisotropy plus gravitational lensing plus some noise. And in their plot you can see with naked eye that there is an excess of the B signal compared to their simulations. Of course you should be careful with plots like that, because you can make them very easily by careful cherry picking and adjusting the scale appropriately. But nevertheless, it's very often reproduced this plot, and I wanted to tell you what it actually shows. So they claim that that at the resolution of 1 degree, there is more depolarization than you would expect without gravitational waves. The next plot is the measurement itself, the power spectrum of the B mode. The black dots correspond to the measurement itself. This solid line corresponds just to the gravitational lens E signal without any gravitational wave contribution. And this curve here is the best fit when we also assume some gravitational wave contribution here. So obviously the line without any gravitational waves doesn't fit in here. And so they report an excess of the signal in the B part of this power spectrum around L equal to 100, which can be attributed to gravitational waves passing through the medium at the recombination time. And they also make their estimate for this tensor to scalar quantity. It's around 0.2. The interesting thing is that this is in slight tension to other results, because there are other ways to estimate this R quantity. The Planck collaboration has made their own bounds on R, and their bounds is that R is smaller than 0.11. So this is one of the reasons why the Bicep2 experiment has encountered so much disbelief. The value of R they got here is very large and in tension with other measurements. These are the rough results of the polarization, still not decomposed into E and P. T, Q, and U are so-called Stokes parameters, a convenient way to measure the polarization fraction in various directions. Now, the most problematic part of the experiment is the systematics part, especially the foreground systematics. By the foreground, I basically mean the emission from the of microwaves at later times, especially microwaves of galactic origin, because our galaxy obviously also emits microwaves, and they can be hard to distinguish from the cosmic microwave background. And moreover, it is known that the microwave emission from our galaxy is also slightly polarized, so it can pollute the signal very easily. This polarized foreground is due to two most important mechanisms: the synchrotron radiation. So our galaxy has its own large-scale magnetic fields, and we also know that there are high-energy particles traveling through space. When they encounter the galactic magnetic field, their trajectory bends and they emit synchrotron radiation. And there is also another very important contribution, which is less understood than the previous one, namely the polarized dust emission. Let me say briefly what it is all about. So, apart from the stars, black holes, and standard astrophysical objects, our galaxy contains a lot of gas, mostly hydrogen, and quite a lot of dust. Not so much is known about this dust. We assume that it is made out of grains of various sizes, from 1 atom basically up to micrometer size. These dust particles are probably made of silicon and oxygen, and probably with some admixture of carbon and iron. If I understand correctly, the silicon and oxygen are something which is confirmed. We know it from the way these dust grains scatter light. We also assume that there is carbon and iron there. We assume that these grains can be very strongly asymmetrical. They don't have to be pulsed, they can be very asymmetrical. And it turns out that some of them may actually be ferromagnetic or paramagnetic. Well, since they contain iron, they can be. It turns out that if a very small grain, which is very asymmetrical, it has 3 very different moments of inertia, which is or ferromagnetic, spins very fast in the galactic magnetic field, 2 things happen on very long time scales. First of all, it turns out that the rotation is unstable for all 3 I forgot the English term. 3 axes of inertia, except for the axis with the smallest moment of inertia. You probably know from the standard mechanics course that the rotation of a rigid body is unstable with respect to the medium axis of the medium moment of inertia, but it turns out that in this part also the rotation with respect to the axis of the largest moment of inertia is unstable. So at the end, after a very long time, the grain will be rotating along the axis of the smallest moment of inertia. And secondly, due to the galactic magnetic field, this rotation vector will be aligned with the magnetic vector of the galaxy. So basically, very strong spin of these particles, and their shape may, on the long run, cause a special alignment of these grains. Namely, they will be aligned in a perpendicular way to the local magnetic field. So the grains tend to spin along the axis of the largest moment of inertia, and they tend to spin in the parallel way to B. But now you can ask yourself where the radiation comes from. And this is the weakest spot of the whole astrophysics of the dust. There are many mechanisms proposed why these dust particles should emit radiation. It may be that it's just the electromagnetic dipole radiation due to thermal motion. It may be vibrations. The vibrations will, of course, be larger along the axis of the largest axis. But all of these scenarios have one thing in common: the radiation will be the microwave radiation will be larger. The radiation will be polarized in the direction of the largest size of this dust grain. And since this dust grain is aligned in the perpendicular way to the magnetic field, the net radiation of this dust will be polarized, at least slightly polarized. Now, this mechanism is known since at least 1970s. So obviously, people dealing with cosmic microwave background were aware of that. It's obvious that you need to filter out this part of the signal from the cosmic microwave background. You can do it if you measure the CMB over many frequencies, because it is known that the cosmic microwave background has a very nice black body spectrum. On the other hand, two other contributions, the synchrotron radiation and the polarized dust emission, follow basically 1 over f1 plus a small number spectrum. So if you measure a sufficiently large number of frequencies, you can just filter out the signal which is due to black body part. The problem is that you need to measure it obviously more than one frequency. You need to measure the radiation in more than one frequency. And indeed, the WMAP, the recent cosmic microwave background measurement measured 5 frequencies. The Planck collaboration, the largest one so far, measured 9 frequencies. But the Bicep2, as I mentioned, measured only 1. So they cannot do it themselves. They need to rely on other people's data. So what they did is they used the data from the Planck collaboration to estimate the foreground due to the polarized dust emission. And this is exactly the point, the most controversial part of their discovery, and this provoked the largest discussion, the most important discussions. Okay, so now let me discuss the criticism of their paper. I'm quoting now here a talk by Raphael Flauger, given in Princeton in May this year. Flauger looked more carefully at the way they used Planck data to estimate the emission due to polarized dust in the part of the sky they were looking at, and found a number of very troublesome things. Namely, first of all, when the Bicep2 paper went out, Planck had not published officially their apparent polarization fraction map officially. So they used a map from the Planck collaboration before it was officially released. Where did they get that from? Well, it turns out that it appeared at one of the talks early this year. And they just took a PDF from that talk and digitalized the map they had there, which does not seem like a very good way to do science, of course. Digitalizing a map from the competing team. Moreover, it seems that they might have slightly misunderstood what the map really showed. Namely, the map did not. In the map, the cosmic infrared background was not subtracted. What is the cosmic infrared background? It's basically the emission from very distant galaxies. Let me go back here. So after the recombination, the galaxies start to form, and the most distant ones are also most redshifted. We don't see them separately. All we see from them is just a uniform glow over the sky, with maximum around the microwave part. It is superimposed on the cosmic microwave background. It's more or less uniform over the sky. It's more pronounced in higher frequencies than in lower frequencies if you look at the microwave part of the spectrum. So it's another thing the people working on the cosmic microwave background have to think about when they measure their signals. Now, it is not polarized. It's basically the emission from very distant quasars and galaxies, which is extremely redshifted. Now it turns out that the map they digitalized was apparently had this part not removed from their signal. Now it does not matter in the regions where the galactic emission is very large, because this cosmic infrared background is very small comparing to the emission from the galaxy itself. But the thing is that the Bicep2 region has chosen their patch of the sky very carefully. They have chosen a part of the sky where it was known that the galactic emission is relatively low. But the problem is that if in this part of the sky the emission is very low, then the cosmic infrared background is something non-negligible. And apparently they do not subtract this part. Slightly later, in May, the Planck collaboration published their map of the dust polarization, of the polarized dust emission on the whole sky, but they did not include the part of the sky where Bicep2 was observing the sky. Of course, the initial response was conspiracy theory, but it did not have to be. So it's simply that the uncertainty of the polarized dust emission is very difficult to estimate accurately in the low emission parts, because the systematic error of this thing is very large, exactly due to the problems with properly measuring the CIB. So Flauber did his own analysis of both data, also using the digitalization of these maps, and just found out that indeed it's very difficult to estimate the polarization fraction from the galactic emission in these regions, exactly because the total emission from the galactic emission is difficult to distinguish from the cosmic infrared background. And these two things are comparable to this part of the sky. So the conclusion of his analysis is that the polarized dust emission in the region they were looking at is probably larger than they assumed. And secondly, that the uncertainty of the polarized dust emission is very large in this region, exactly because of what I said. It's difficult to distinguish between CIB and the polarized dust emission. So the signal may be due to gravitational waves, but you cannot exclude that this is just pure foreground. So this is a picture from his talk. Here are the points measured by the Bicep2 collaboration. This line here corresponds to their best model of the foreground emission. Now, Flauber's group has very different estimates for this foreground emission, namely, it corresponds to this stripe here. Note that it's much higher that it's significantly higher than what Bicep2 presents here. And secondly, the uncertainty, the error bar of this emission itself is very large. It's not a curve, it's a rather broad band here. So it seems that all these 4 points seem to lie within the foreground uncertainty part. So Flauger is very diplomatic in his talk, and just to quote his conclusions. So Bicep has provided us with the deepest maps of any patch of the sky at the 150 MHz and has detected degree-scale B modes. That's true. According to all estimates, foregrounds may be small enough to detect a large primordial signal at 150 kHz without foreground subtraction, but the uncertainty on the foreground is large, and measurements at other frequencies, especially about 150 kHz from time, seem important for a definite measurement. So this is very diplomatic, but I think that what he says is that the data they have provided themselves just from one single frequency band is not enough to really distinguish between the foreground emission and the cosmological emission in their measurements. He also tried other clever ways to estimate the galactic emission. For example, from the neutral hydrogen line, you can measure how much neutral hydrogen you see in a particular direction, and the assumption is that the dust is somehow related to the neutral hydrogen. This way, you can estimate how much dust you see in a particular direction and try to estimate the polarization fraction from that. And all his analysis points to the same direction, that basically the no gravitational waves hypothesis is not ruled out yet. There is also another paper done by two independent researchers who analyzed the. So the Planck collaboration has. I haven't said that probably. The Planck collaboration, which runs a huge satellite which measures very accurate cosmic microwave background over the whole sky. They have finished their data. They have finished their observations. They are now analyzing the data and releasing once a month another paper about various properties of what they have seen. And using what's publicly available now in the Bicep part, this group performed their own analysis of the data. Well, they basically repeat the criticism about the use of the preliminary dust, of the Planck preliminary dust polarization map. They reanalyzed the data, assuming certain things about the power spectrum of the dust emission. I'm not quite sure where they get this power spectrum from, but they quote somebody. Again, the result is that the hypothesis of no gravitational waves at the moment is slightly favored, and all you can do is to put bounds on this tensor to scalar ratio that's smaller than 0.11. And of course, they claim that at the part of the sky Bicep2 was looking, you certainly need more frequencies to separate the foreground. This may be possible when Planck releases their full data next year, but it does not have to be the case. They also analyzed the most pessimistic scenario that the polarization fraction is very large, and in that case, even the Planck data may not be enough to resolve whether the Bicep2 was really seeing the gravitational waves or not. And the last paper I want to mention appeared in April. It's a very interesting paper. It's written by 3 European researchers from Denmark, Britain, and I don't remember where from. They were discussing a thing called galactic radio loops. So galactic radio loops were discovered in radio frequencies in the 1970s, and they're basically regions of enhanced emission of radio waves which form circles in the sky, very large circles, comparable to the size of the full sky. It is thought that they are a galactic source, and they are rather faint, but what we believe is that they are just supernova remnants. What happened is that just a supernova exploded at some point. It created a shock wave which passed through the interstellar medium. It was strong enough to sweep both dust and gas from a huge ball of the galaxy, and at the same time create a shell of higher dust and gas higher dust and gas density. And now this gas and the emission from the galactic foreground, and now the fact that we see a circle here is just due to so-called blink light, namely when we look at these directions, we cross a larger part of high density material than we see here. So we simply see this shell of larger. We see the shell of larger density of dust and gas in our galaxy. And since 1971, 5 such loops were observed on the sky. Some of them were in fact correlated with regions of larger supernova explosions. Also, these loops were at least partially observed in other frequencies, including X-ray, gamma, and microwave. Now, in this paper, the authors simply tried to see whether these loops have been filtered out from the WMAP maps of the cosmic microwave background. They did a statistical analysis of the number of peaks near the known loops, and they have shown quite convincingly that these things were not filtered out correctly. If you look very carefully, you see, even though in principle the galactic emission is supposed to be filtered out from the final maps, it's not quite filtered out. But in the very last sentence of their paper, they relate to the Bicep2 collaboration paper and just notice that 2 of the known loops crossed through the patch of the sky the Bicep2 was looking at. And it seems that Bicep2 didn't take this into account at all. So that seems like another thing that's... Okay, it is not clear to me whether the emission from these shells should be polarized or not, but at least before Bicep2 collaboration gets a Nobel Prize, they should comment on this thing as well. Okay, so here I just restate what I said before. Basically, if you look at the CMB signal from the WMAP collaboration, if you look very carefully and perform statistical analysis of the signal, you see at least some of these loops quite convincingly. They even managed to comment on the physical mechanism of the radiation coming here. What fits more is the magnetic dipole radiation of the dust. So this dust is by itself some magnetic dipole moment. It also vibrates and spins, and the magnetic dipole radiation, very faint, may account for, it's the best candidate to account for the signal from these loops. And they managed that 2 of these loops pass through the region of the sky Bicep2 was looking at. And of course, this is another thing the Bicep2 collaboration should rule out before their discovery is really acknowledged by the rest of the community. Okay, so let me finish with a summary. So the Bicep2 collaboration measured the polarization of the cosmic microwave background radiation in one frequency band, around 150 gigahertz, over a 2% patch of the sky. And they looked at one particular mode of they looked at the B mode of the polarization spectrum. They were interested in more or less 1 degree features of this, size features of this B mode map. The origin of the polarization of the CMB. Well, there are many mechanisms, but the most important ones are the anisotropy of the radiation due to temperature differences in the medium, plus the scattering on electrons of the recombination time. The anisotropy itself is partially due to gravitational waves. Bicep2 was exactly trying to look at the part of the signal which is due to gravitational waves. They did detect an excess of the B mode at the expected L of 100, but the problem is that it seems so far that they didn't take the foreground emission into account in a proper way. This is less about the synchrotron radiation, more about the polarized dust emission. They used their data from unreleased plots by Planck it's possible that they misinterpreted some part of the data. And secondly, it seems that the uncertainty of how large this emission, this polarized emission is, that clearly cast doubt on this result. So this problem may be resolved quite soon when Planck starts to release their data officially, and also some other experiments looking at the B-mode polarization of the CMB start to give their own data, and this should happen next year. So by the end of the next year, we might have this problem completely resolved. We will know for sure whether the result reported by Bicep was a fizzle or whether it was a real discovery. Thank you.
I'm very grateful to our speaker for making the effort to present us with this analysis. Just one small question. What is special about L equals 100? This is a pure number. Is there any way to...
It's a beautiful number.
10 times 10, I know. So is there something that distinguishes the region around, of course, not just one number, but the region around L equals 100? It's a very high, not angular momentum really, but the spherical harmonics. So can we really say something about which spherical harmonic it is by observing on the very narrow arc?
That's a good question. Okay, this has something to do with the spectrum of the scalar and the tensor perturbations in the universe, but I didn't go that deep, to be honest. I just took this value from the literature as given. I may look it up if you're interested. I don't know at the moment.
This whole analysis in terms of spherical harmonics is very mysterious.
Yeah.
Why they play such a role?
Just a small...
More questions?
I have a question about this supernova, because I didn't quite get the last point about this radio loop. Does it originate from a collection of supernovae? How does that usually I mean, not in our galaxy, yes?
No, it's about our galaxy.
In our galaxy,
Yes.
Such a large radio loop of the whole sky map.
Yes. Or at least that's what the authors were claiming. It's not very strong, it's rather faint. It's rather faint.
Yeah, we see this cone here, and this is what makes the loop.
We don't see the cone. Okay, so let me make a picture. We stay here. The supernova explodes here. It sends a shockwave through the medium. Behind the shockwave there is a rarefaction. There's a rarefaction problem of the interstellar medium, and of course there is a part which has a larger density. Yes, all this dust now emits radiation in all directions, but as we see here, our eyesight passes through a deeper column of this dust.
A single supernova?
What they say is that there are most likely supernova remnants, and that one of them has been correlated with a place with a large number of supernova explosions in our galaxy. So I don't think anybody managed to pinpoint a particular supernova,
Okay, yeah, that's what I'm asking about.
Which created a particular latent. So these things are just the beautiful. So you can think about the beautiful pictures of supernova explosions from the Hubble telescope. This radio loops is what this will look like in, I don't know, many millions years from now. You will not see anything except for faint radio emission from a shell.
Thank you once again.
Yeah.
policzyć. Bardzo dobrze to wypadło. No i trochę jednak pan skorzystał chyba. Trzeba wiedzieć takie rzeczy, jeśli się jest, szczególnie jeśli jest relatywistą.
To jest bardzo ładne wszystko, natomiast oczywiście tutaj ewidentnie grało rolę to, że oni musieli coś głośnego odpalić, żeby dostać finansowanie.
No właśnie.
Więc dlatego podchwycili cudzą łapkę, zaktualizowali.
To moje pytanie jeszcze właśnie się wiąże też z tą skalą, no to są straszliwie wysokie te L tutaj. W ogóle...
L po prostu odpowiadają wielkości na niebie.
Albo tym pikselom, który...
To tak, ale kosmologicznie one odpowiadają po prostu wielkości, rozmiarom kątowym różnych rzeczy, które widzimy dzisiaj na niebie po 18-14 miliardach lat.
Tak.
Była jakaś, oczywiście te akustyczne oscylacje wyróżniły pewną skalę długości, skalę tego pierwszego piku w momencie rekombinacji, no to teraz widzimy.
Czy z tego przeglądu literatury, który pan zrobił, to wynika, że ktoś rzeczywiście policzył tak z pierwszych zasad, jak wygląda propagacja światła na fali grawitacyjnej, bo wydaje się, że to można porządnie zrobić. Mamy falę grawitacyjną, która oczywiście krzywi tę geometrię.
Przypuszczam, że korzystamy tutaj z tych starych prac Isaacsona, który propagację fal grawitacyjnych i jej oddziaływanie z materią opisowe jeszcze w latach 60. Czy ktoś coś bardziej skomplikowanego robi? Tego nie.
No bo ja widzę ciągle tylko takie machanie rękami, że tutaj to w jednym kierunku się rozciąga, w drugim się ściska ten kwadrupol tej fali grawitacyjnej i że to jest ten efekt. A to przecież można policzyć dokładnie.
To znaczy można zrobić dwie rzeczy. Wziąć
Tło w postaci fali grawitacyjnej.
No można,
to
są jakieś małe parkole, coś takiego. Przypuszczam, że ktoś to już zrobił, ale nie widziałem. To jest na ogół robione w liniowych czy podobnych przybliżeniach.
Nie, oczywiście liniowe jest zupełnie dobre. Ja się pytam pana Mikołaja.
A ile oni mają tych pikseli tam? Mniej więcej.
Ale to nie jest tak, że on patrzy cały czas w jednym punkcie. On tak przesuwa się. Nie mówiłem dokładnie, jak wygląda obserwacja. Oni tak wodzili po tym całym prostokącie tego zakosami.
No dobra, ale no to dobrze, a już na tym obrazku to ile tych pikseli jest?
4 razy 250, około 1000. A każdy piksel zabiera...
Ale na całym tym koło 1000?
A każdy piksel...
No i co, i na podstawie tych 1000 pikseli można równe 1000?
Oni dużo chytrzej tego. Oni tym obwodzą bardzo powolutku.
Aha, czyli w jednej chwili mają koło 1000.
Tak.
No dobrze, ale to
ileś tam setek razy to nie było. Co więcej, oni obracają ten cały detektor, żeby pozbyć się systematyki związanej
Ziemia się obraca.
Ziemia się obraca to też. To oczywiście gdzieś pływa. Musieli.
I wreszcie mogli...
Nie, po to jest na biegunie, żeby się nie obracała tam.
Nie, na biegunie jest z innego powodu. Na biegunie jest po to, bo jest sucho. Bo jest sucho. Woda jest bardzo niebezpieczna dla takich obserwacji, bo woda ma dużo pików mikrofalowych. A oprócz tego biegun północny jest na wysokości 4000 metrów nad poziomem morza, co jest o tym też nikt nie wie, ale to jest taki lodowy płaskowy.
Tak, mi się wydawało, że...
Mam kolegę, który oczywiście nie w tym eksperymencie, bo to 20 lat temu, on spędził prawie rok tam na tym, jak oni odkryli to na początku, to prawie rok tam spędził.
No, bardzo dobrze.
Ale to w sumie, jak pan rysuje te obrazki, to ile tam jest pikseli?
U nich?
No tak mniej więcej, no.
Pojęcia nie mam, przepraszam.
No dobrze.
Na pewno jest to też praca, mogę pracę panu wyłączyć.
Dobrze, to kiedyś.
Ale nie, systematyka dotycząca samego instrumentu tak jest bardzo dobrze zrobiona.
Potem jacyś kelnerzy to opublikują.